Good evening, everyone. Welcome to this tutorial lecture on discrete mathematics. We couldn't have this session on Monday because Monday being a holiday, so I'm taking this class today. So today we'll be discussing week 10 assignments from the previous iteration of this course, and it is mostly related to inclusion-exclusion principle. So I'll start by sharing my screen. Okay. I hope the screen is visible to everyone. So let's get started. So coming to the first question, in how many onto functions are possible from a set of 7 elements to a set of 4 elements? So this is the domain set, and this is the range or codomain. Since it is a domain, it means that every element has an image in codomain. That is the very definition of domain. Now, can anyone take a guess as what onto functions are? So you have studied onto functions in previous lectures. So can anyone just recall what onto functions are? Anyone?
Every domain has a image.
Uh, Right. So onto functions are basically every element in the codomain has a pre-image in the domain. Every element in codomain has at least one pre-image in domain. So some examples I can show you is this. So let's say you have, so this has a image, let's say this one. This may be connected like this, and this. This is onto this. Suppose this is, so in this second case, this is not onto because all the elements in the codomain, so this is domain and this is codomain, domain and codomain. So in the second figure, in the codomain, you can see there exists one element which does not have a pre-image in the domain. So there that is not onto. So now we have been asked to find out such functions where the size of the domain is 7 and the size of the codomain is 4 and such that the function is onto. Now, before we go on to onto functions, so given a domain and a range set, so given a domain of size m and codomain, that is codomain of size n elements, total number of functions that we can generate, that we can generate. How many total possible mappings can be there? Can anyone recall the formula of this? It is actually n to the power m. So how this formula comes, I'll just briefly tell you. So it's, let me push it.
சரிம்மா போயிட்டு வாமா.
Yeah, did you say anything?
So sigma I varies from 0 to n minus 1 the whole power I nc1 n minus I the whole power m.
Uh, that is the total number of functions that we can generate, you are saying? No, no, I am asking not onto function. I am telling just the all possible type of functions that we can generate if the domain is of size m and the codomain is of size n. So
Okay. Sorry, sis.
yeah, yeah. So I'll just briefly tell you how this comes if anyone has a doubt of it. So is you take the domain set, you have uh, m elements and each has an image. That is because they are in the domain. Now for each element in the domain, each element can be mapped to a function. So from one element it will map to only one other element in the codomain. So you have this codomain over here. So from one element in the domain, you cannot have multiple mappings in the codomain. So that thing is there. So for each element can be mapped to one element in codomain. So that gives us n options. So for every element in the domain, it has n options to pick from. So the n options are the n elements in the codomain. So therefore, total options, total combinations. So for every n m elements have n options. So therefore, we have n to the power m. So this is like a coin toss experiment. So if there are m uh, people who toss a coin, so total possible outcomes are so for each person the total possible outcomes can be 2. So for the total all the m people it will be 2 to the power m. So similarly in this case every element in the domain has n options, therefore it is total combinations could be n to the power m. So this is how we can generate functions. That is all possible functions that we can generate. Now, all possible functions are not onto functions. So how will we? So an exception could be like this. So you have, let's say, 7 elements: 1, 2, 3, 4, 5, 6, 7, and you have 4, 1, 2, 3, 4. So a mapping could be like this: domain, codomain. It can be like this. So this mapping, this is a valid mapping. This is a function counted in this n to the power m, counted in when we in the all possible set of functions. but not onto. So such a function is not onto. So we'll have to remove such functions from the set. So now that we know what we have to do, so we'll basically say that, let's say C1 is when element 1 from codomain does not have an preimage, does not have pre-image. This is the event C1 that element 1 does not have preimage. C2 is element 2 and C3 is element 3 and C4 is element 4. And so we basically have to find out uh, so what we have to find out is n of C1, not C1, not C2, not C3, and not C4. So it means that all of the elements in the codomain have a preimage, which makes the function onto. So this is by simple inclusion-exclusion principle, we have n, which is the total number of functions, minus n of C1. So we'll sum it up like this: n of C1 plus n of C2 plus n of C3, n of C4, plus we'll have the combinations of uh, two combinations. So n of C1, C2, when C1, C2 means that both element 1 and element 2 does not have a preimage in the domain. So that is what is meant by C1, C2, n C1, C3, and so on till n C3, C4. And finally, we have this three combinations. So we'll have n C1, C2, C3 plus n C1, C2, C4, and so on, various combinations of n C2, C3, C4 maybe. So, and finally, we'll plus n of C1, C2, C3, C4. This is the inclusion-exclusion principle. So we call, let us call this as S0, this box as S1, this as S2, this as S3, and this as S4. So that gives us S0 minus S1 plus S2 minus S3 plus S4. Now to compute all of them, so S0 is basically 4 to the power 7. S1 is the sum of NC1, NC2. So it is uh, basically selecting four elements out of so we are selecting one element out of four elements. So we can do that in four choose one way, and the NC1, NC2, NC3, NC4 will all be same. So NC1, this, so NC1 is when you remove one element from the codomain and find out all possible functions. So the formula is basically n minus 1 to the power m. So it would become 3 to the power 7. So this is also equal to nc2, nc3, nc4. So that makes it 4c1, 3 to the power 7. For S2, we'll have to pick two elements. So we can do it in 4 choose 2 way. And for it is NC1, 2, let's say. So NC1, 2 is basically we remove two elements. So it would become 2 to the power 7. And this is same for all C1, C3, C3, C1, C4, and so on. NC3, C4. It will remain same. So S3 would be picking three elements and NCC1, C2. Wait, S3 would be 4 choose 3 and C1, C2, C3. So that would be 4 choose 3. We are removing three elements, so we are left with one. And finally, S4 is when we are removing all the four elements. So none of the elements in the codomain have a pre-image in the domain. So that would be 0 to the power 7. So now if we add it up, so what we get is 4 to the power 7 minus 4 choose 1, 3 to the power 7 plus 4 choose 2, 2 to the power 7 minus 4 choose 3, 1 to the power 7 plus 4 choose 4, 0 to the power 7. So if you plug it in, so this would come out to be 8400. So this is the answer for this question. So 8400 would be the right answer. So option B is the right answer for this question. I hope this is clear to you. If the inclusion exclusion principle is clear to everyone, I think this is pretty straightforward. So mainly I focused on how this onto functions are being generated. So this is just a recap. If anyone forgot what onto functions are and how they are different from normal functions, so that is why I spent so much time in finding each element. But it is a pretty straightforward question. I hope it is clear. Uh, we'll move on to the next question. If you have a doubt, you can ask me or you can ask at the end as well. Okay. So next question is how many positive integers are between 1 and 500, including both 1 and 500 that are not divisible by 3, 6, or 9. So we'll basically call this C3 is integers divisible by 3, C6 as divisible by 6, and C9 as divisible by 9. So again, what we have total in, we'll have to find out n, not C3, not C6, and not C9. So that is basically n, that is n is 500. So we have 500, the pool of numbers is 500. So n minus, again we'll have this nc1 plus n, sorry, nc3, nc6, nc9, and plus we'll do it for the uh, two cases, that is it is divisible by, it is divisible by both 3 and both 6. n C3 C9 and so on, and finally that is minus of, that is divisible by all of them, C3 C6 C9. So this is also again just numerical example. So the main point is how to find out this NC1. So n is 500, that is already given. NC3, so now NC3, NC6 and NC9 will be different. So NC3 is basically the number of number of integers divisible by 3, that is lies between 500, 1 to 500. So we'll basically take the floor function, lower integer function. So we'll divide by 3 and take the lower one. So it is around 166, I think. Yeah. So NC6 would be 500 by 6, which is how much? 8, 83, I think. And NC9 would be 500 over 9. We take the floor of it, and this would be uh, 55, I think. Yeah. So now this is, now for the two cases. So let's say NC3 and C6. So there would be 6 combinations you'll have to find out. So for 3 and 6, what we do is we, that is divisible both by 3 and 6. So basically we'll have to take the LCM of 3, 6, which is 6 itself. So that is 83 again. So let's say if we do for 3 and 9. So LCM of 3 and 9 is 9. So it is 500 by 9, 55, and C6 and C9. Now this is interesting because C6 and C9, the LCM is, so 9 is not a multiple of 6. So the lowest common multiple will be 18. So 18, I think, 2 ja 36, 14, no, 140. So 27 would be the answer. So this is how you find out for 3. And for the, when it is considering all the C6, C3, C6, C9, it is, we'll again take the LCM of 3, 6, and 9. So it is LCM of 3, 6, and 9. So that would be 500 over 18, because 18 is the lowest multiple of 6 and 9, and 3 is also uh, multiple of 18 is also a multiple of 3. So this is again, I think, 27. So this is, if you just numerically substitute it, so what you get is this answer as 334. So this is just a numerical substitution, and I hope this is a straightforward question. I hope it is clear to everyone. Moving on to the third question, again we have this derangement problem. So we have 6 people who went to a birthday party, and they leave the coats in the entrance, and they choose their coats blindfolded while leaving. In how many ways can they wear them so that no one wears their coat, so that no one wears their own coat? So it is a classic derangement problem. So we'll have to find out basically the number of derangements. So again, most of you already who have seen the lectures know that how it is calculated, but just for completeness, I will briefly discuss how it is derived. So again, we'll consider C1. So okay, so n is the, what is the total number of permutation of these six quotes. So we have, let me draw the diagram. So we have, let's say, quote. So we name the, do it like this. So we have the person one, two, three, four, five, six, and this is the quote number. So this is the correct quote. So let me put it with green. So correct, one, two, three, four, five, six. So it means that person one is wearing the right. So the derangement would be, derangement would be when uh, the, the person is not wearing the his own coat, and none of the persons are wearing the right amount, the right coat. So let's say one is wearing two, two is wearing five, three is wearing six, four is wearing one, and five is wearing three, and six is wearing four. So here, uh, this is a derangement. Okay, so we have six persons, we have six code. So what is the total combinations, total permutations? Can anyone say what is the total permutations of six codes?
6 factorial.
Right, so it's 6 factorial. Okay, so now let us again, for this inclusion exclusion principle, what we'll see is again, uh, we will define this sets C1 as person one wears his or her own coat, correct, his or her own coat. We do not know what about the other people. So that is the beauty of the inclusion exclusion principle. So while calculating C1, we don't consider whether the other persons have worded correctly or not. We are just interested in person one. So we assume that person one wears his own coat correctly. So similarly, C2 is for person two, and the thing goes for C6, that is person six wears his own coat. So now again, this is equal to n, so total. So what we have to find out is again C1 not C1, not C2, and not C3, and not C4, and not C5, and till not of C6. So that is again by inclusion exclusion principle. It is n minus the singletons in C1, C2, C6 plus the couplets C1, C2. So C1, C2 means that 1 and 2 have worn their codes correctly, but the rest we don't know. So that is N C1, C2, N C2, C3, and so on. And let's say N C5, C6. Then we subtract again from, we are taking three at a time. So C1, C2, C3, and so on, N C C4, C5, C6. Now the four people we are considering together in C1, C2, C3, C4, and in, let's say, C3, C4, C5, C6. Again, five people, C1, C2, C3, C4, C5, and C2, C3, C4, C5, C6. Adding, and we are considering all. So the case where all of them wears them correctly, C2, C3, C4, C5, C6. Now, to find out, let me- okay, to find out NC1. So NC1 would basically means one went to the one wears his coat correctly, but the others we don't know. So we have five people, and five people can wear. We have five coats, so five coats can be arranged in 5 factorial ways, and one is wearing his correct coat. So one is fixed, and the other five are variable, and the same applies to all C2 to C6. They are all equal. So basically. Uh, we'll have six choose. So we are picking one person at a time. We are telling that this person is wearing the coat correctly, and the number of ways that person can wear correctly is 5 factorial, because the other person, we have five other persons left, and they can, the total permutations of their codes will be 5 factorial. Similarly, if we choose in C1, C2, so means we are fixing two, and the others can vary. So we have 4 factorial. And this is also the same for other uh, people. So it is C2, C3, and so on. So in C5, C6, let's say. So they are all equal. So again for C1, C2, C3, three people, we are left with three other people. So 3 factorial. For 4, C3, C4, it is 2 factorial, and for 5 it is. So five people are wearing their coats correctly. So it obviously implies that the other one is also wearing their coat correctly. So that is 1 factorial, which is 1. And where uh, all of them are wearing correctly, that is also 1, because it's 0 factorial. So it's 0 factorial, it's 1. So if we plug it back in, so in not C1, not C2, not C3, not C4, not C5, not C6, that would basically be, so first we have n, which is 6 factorial, because that can be quote can be arranged in 6 ways. Next we minus the number of ways we can select one out of them. So 6, choose one. So we have 5 factorial. Then we choose two people and give them their correct quotes. Next we minus 6, choose 3, 3 factorial, plus 6, choose 2, 2 factorial, and choose 1, 1 factorial, and 6, choose 0, 0 factorial. So this is the derangement number. So it is basically 6 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial plus 1 by 6 factorial. So this term in the bracket is a truncated term of the series 1 by e. So this is approximately 6 factorial by e, which is around 265. So uh, this expression, this without the e, that evaluates to 265. And if the number like this number 6, if it goes large, we can approximate as 6 factorial by e. So it e is around 2.71. So this derangement of a number, so derangement of a number, that is n factorial uh, over e, would be around n factorial by 3 and n factorial by 2, and closer to this left bound. So n factorial it is closer to n factorial by 3 than to n factorial by 2. So if you have been given a problem in the question to find the number of derangements, so all you have to do is find the n factorial. So you have n objects, you find n factorial and divide it by 3 and check and divide it by 3 and divide it by 2. So it should lie between the those two, and it should be closer to the bound that is divisible, that is on division by 3. So that is how easily you can select in MCQ questions. So for this, the option would be B, 265. So uh, D of 6 is 265. I hope that is clear. Coming to the next question. So this is a simple question. So consider the following set. We have A, B, C, and we'll have to find out what is the cardinality of A union B union C. So when we take union, we do not repeat the elements in the set. So we basically uh, consider in the A union B union C. So we'll select all those elements from A, B, and C. All the elements from A, B, and C will be selected, but without repetition. So I'll show you which elements are selected. So I'll color it with green. So 4 is selected, 3 is selected, 6 is selected, 2 is selected. Now Mumbai is also selected, but this 2 in B is not selected because it is already been selected when we selected the elements of A. So we won't pick 2 again. Next 5 is selected, Delhi is selected, working is selected, cooking is selected, and Delhi is not selected because Delhi is already been selected when we were considering set B. So basically what is the cardinality is number of elements in this. So it turns out to be I think 9, 4, 3, 7 to 9. Yeah, 9. So the right answer for this question is option C, 9. It was a pretty straightforward question. Come to question number 5. So there are three OTT service providers in a region populated by 20,000 people. An individual can subscribe to uh, any number of service provided, but assume that each person is subscribed to at least one of the three service providers. So there are no person who does not have is not subscribed to any of the providers. So we say that 10,000 people are subscribed to Netflix, 13,000 to Prime, and 9,000 to Hulu. If there are 9,000 people who are subscribed to at least two OTT providers, then how many people are subscribed to all three? So this is a little tricky question. So I'll draw the sets first. So this is, let's say Prime. This is, let's say, Hulu. And let's say this is Netflix. Now our question is, what we have to find is how many people are subscribed to all three. So basically this region. So let us call this X. That is here, the dotted region. Okay. Now, uh, what we can see is this, uh, what we know is union P H N, that is equal to 20,000, because every person is subscribed to at least one. So the whole union would include all the person in that region. So that is 20,000. Now this P of H union N can be written as P plus H plus N minus P, uh, I think it is union H, sorry, intersection H minus P intersection N minus H intersection N. Hmm, I think these are the three, and plus of P intersection H intersection N. So our goal is this term that is lies in the intersection of all the three sets. Now, what we have been given this information that 9,000 people are subscribed to at least two OTT providers. If there are 9,000 people who are subscribed to at least two OTT providers, so they are saying that people in this region. So I'll draw with this dash. So this dash plus dot is, they are saying it is 9,000. So basically, what is this region? This combination of dash and the dot that is lies in the intersection. So it is this. So it is in sum of this plus sum of uh, this plus sum of this. So now we are counting this X region, that is the dotted region, thrice. So we are counting it once here, once here, once here. So we'll have to remove it. We'll remove two twice of it. So that uh, is it clear why I am removing uh, twice? So this is 9,000. So what I am, when I am doing P intersection H, I am considering this region. So this will I that is the region when that I am considering when I am considering P intersection H. So there I am considering both the dashed portion and the dotted portion. So dotted portion is being counted once and the dashed portion is being counted once. So now similarly, for when I'm doing P intersection N, I'm counting the dashed region plus the dotted region. And H intersection N, I'm counting the dashed region and the dotted region. So this dotted region is being counted thrice, but it should have been counted only once. So we are removing twice. That's why. So twice of P intersection H intersection N, that is N. So we call, let us call this as X and this as X. So if we, so this term can now be written as 9,000 plus 2x. And from this, if we substitute back in this equation, so this equation now gives us P plus H plus N. So P was people who are subscribed to Prime, that is 13,000. So this on the left hand side it is 20,000. On the right hand side P is 13,000. Hulu is 9,000. Netflix is 10,000. And we subtract this 9,000 plus 2x and we add an x to it. So this would turn out to be, say, this 9,000 and this 9,000 cancel. So it's 23,000, 23, 3 is what it, mm, minus x. So x equal to 3000. So therefore the right answer is option D. So the critical part of this problem was this step of why we are subtracting twice the intersection. Otherwise, it is a pretty straightforward question. I hope it is clear to all. Let us move on to the next question, which is similar to the previous question. So a form, a survey has three fields. A, B, and C is handed out to 50 participants. Each participant has to fill at least one field in the form. 12 participants did not fill the field A, 14 did not fill B, 10 did not fill C, and 25 participants filled all three. So how many participants exactly filled exactly one field? So again, I will draw the diagram. So we have, let's say this is A. So this set A represents all the people who have filled this this field A. We have B, and let us say we have C. Now in this figure, it is 25 over here. That 25 participants have filled all three fields, and the union of these. So there are no people outside of the union of ABC because everyone has filled at least one field in the form. So now what they wanted to ask is how many participants filled exactly one field. So this is the number of parties. So people who filled only A are this. People who filled only B are these. And people who filled only C are these. So they are asking us to find what is the cardinality of this dotted region. If, and we know that the central region has 25. So, so let us call this dashed region. So we have basically two regions. So we have this dashed region and the dotted region. So dotted region, we cardinality equal to x, and the dash region cardinality equal to y. Now total there are 50. So what we have is x plus y plus 25 is 50 because there is no one outside of this. So x plus y is 25. Now look at this uh, empty. So now let us count uh, blank fields. So for A, it is, so when we count the blank fields, so that is the number of field that is not filled. So there are 12 blank fields for A. So in uh, 12 uh, of those forms, A was not filled. In 14 of those forms, B was not filled, and in 10 of those forms, C was not filled. So there are total of 36 blank fields in all the 50 forms. Now this person X, so in the dotted region, will leave two blank fields because it's filling only one of the field, and there are three fields, so it he or she will leave two fields, and people in this dashed region will leave uh, one blank field, and people in this intersection, that is where it is written 25, they will leave no field because they have selected all three fields. So from this uh, data, we can see that there are total leftover fields is 36. So it is 2x, because x are the number of dotted regions and they are leaving two fields, plus y. Y is the cardinality of this dashed region and they will leave one field. So that should be equal to 36. So from simple algebra, x turns out to be 11. So that is the cardinality of people who have filled exactly one field. So option A is the right answer for this question. I hope that is clear to you. Simple set theory applications, so nothing complicated. Coming to the seventh question, so which of the following can be a valid Rook polynomial for a 5 cross 5 chessboard? Now, in a 5 cross 5 chessboard, there are 25 positions. So, one rook can be placed in how many positions? One rook can be placed in how many positions? Can anyone take a guess? So we have 25 positions on the chessboard and we have one rook. So in how many ways can you place it? Anyone?
25 ways.
Yeah, you're right. So there are 25 positions and you have one rook, you can place anywhere. So there are no other pieces on the board. So the right answer is 25. So in the polynomial, the the coefficient of x should represent the number of places, number of ways one rook can be placed. And if you look at these coefficient, that is the coefficient of x in the polynomial, none of them are 25. So the right answer, the right answer is not in any of A, B, C. So none of these is the right answer. So this is just a question where you can, this does not actually find out the entire Rook polynomial, but it eliminates out the options which cannot be valid Rook polynomial for a 5 cross 5 chessboard. So for actually to find it for a 5 cross 5 chessboard, it would be much more extensive, and so you can try it out on your own. But this problem was just to neglect those answers which cannot be right. So you can just easily look at, instead of just finding out the entire Rook polynomial, you should first try to look at in how many ways one rook can be placed and if any of the answers matches, and then you could have proceeded further. So this was a simple question. Coming to question number 8. So let us say what is an alike prime is a number which is not divisible by 2, 3 or 5 and is composite. So the first three alike primes are, for example, given as 49, 77, 91. So you are given the information there are 1229 prime numbers less than 10,000. Now, how many alike primes are there and are less than or equal to 10,000? So, our again, it is an inclusion exclusion principle. So, what we do is n. What is n? N is 10. We'll consider uh, all composite numbers. So, uh, we are not so alike primes are composite. So, we will have to remove the prime numbers 1, 2, 2, 9. We'll have to remove, but we'll just for now we'll add this 2, 3, 5. So we are adding 3 for this set. We are including, we are considering composite numbers and 2, 3, 5, and we are removing 1 from this. So this one is for 1. So 1 is neither prime nor composite. So we are not interested in 1. So we are removing 1 and we are considering the other composite numbers plus these three prime numbers. So why we are doing it is because I'll define this sets. So C1 is uh, numbers divisible by 2. Numbers C2 is numbers divisible by 3. And C3 is numbers divisible by 5. So this C1, this set C1 includes 2. This set includes includes 3, and this set includes 5. So what we have is, if we did not, so this is why we are adding these three prime numbers into the set of composite numbers. Composite numbers. So we are including this 3 in the set of uh, composite numbers because we'll have to remove the C1, C2, C3 from it. So the we are basically interested in this is n, and we have C1, C2, C3. So C1, C2, C3. So to make sure that this n contains all the elements of C1, C2, C3, we are putting these three elements 2, 3, 5 in this list. That is the key takeaway of this problem. And from here, the problem is pretty straightforward. What we have to find out is now n of C1, not C1, not C2, and not C3. So that is would be n minus n of C1, n of C2, n of C3. And similarly, we'll have to remove, we'll have to add the twin. So C1, C2 plus n of C2, C3, n of C1, C3. I think these are the only three possible. Now we'll subtract n of C1, C2, C3. So that is all the numbers that are divisible by both 2, 3, and 5. So like we found out in a previous question, so when we'll have find numbers divisible by a number, we'll have to uh, take the floor or the lower integer value up on dividing that number. And if we have two or more numbers, we'll have to divide it by the LCM of it. And it is a pretty straightforward if you put the value. So this turns out to be 1439. So you just solve for this NC1, NC2, NC3, and these terms you find out, and if you apply, it would be 1439. So option C is the right answer. I'm not doing this in interest of time. So if you have any doubt, you can obviously ask me how this. Now coming to question 9, if n is sufficiently large, which of this is a good approximation of the possible derangement in n objects? So like we discussed in previous derangement question, so it is n factorial by e. So what it turns out is like this. So d of n would turn out to be n factorial by 1 minus 1 by 1 factorial plus 1 by 2 factorial 1 by 3 factorial and all the way up to uh, minus 1 to the power n 1 by n factorial. So this is a truncated version truncated form of 1 by e. So in actual 1 by e, n tends to infinity. So limit, so this series, so let us call this series as S of n. So limit n tends to infinity, S of n is 1 by e. This is the, and so here they are asking is n is sufficiently large. So that is what they're telling, that when n tends to infinity, so S of n becomes 1 by e, and that is equal to n factorial by e. So derangement number dn is n factorial by e. So I think it is pretty clear. I have already discussed this in a previous question. Let us move on to the final question. So how many integers are there for this equation xyz equal to 15, where we have this x less than 9, y less than 7, and z less than 3. So again, the easy way to do is n is all integer solution where x greater than equal to 0, y greater than equal to 0, and z greater than equal to 0. So in this question, it is assumed that non-negative. So they have not uh, mentioned it. So integers can be negative also. Just uh, for your understanding, it is assumed that they're talking of non-negative integers where x is less than 9, y is less than 7, and z less than 3. So that's why we are counting n as all integer solutions where x is greater than equal to 0, y is greater than equal to 0, and z is greater than equal to 0. So that would be basically we have three stones and three sticks. So the sticks and stone problem. So it would basically be we have a total of three numbers, and we'll have to place two uh, plus signs. So we have two sticks, so two plus signs and three numbers. So that is basically, I think, uh, three integers is 3 plus 1, and that should add up to 15, and we'll have to pick. Uh, so these are the total number of spots, and we'll have to choose 15 or 3 minus 1. So that is basically 17 upon 15. So this is n, all integers. I hope this is clear. So this is from uh, sticks and stones example. Print. So we have basically this x, y. So we have, let's say, 15 stones, and this plus signs are the sticks that we'll have to place. So in how many? So total there are 15 plus 2 plus signs. So if there are n integers, we have n minus 1 plus sign. So that's how we have 2 and plus 15, and we'll have to place total slots are 15 plus 2, 17, and we'll have to pick two of these any uh, how we place this 15 uh, stones in this 17 slots, that will give us all possible solutions for x greater than equal to 0, y greater than equal to 0, and z greater than equal to 0. Now we again, like our inclusion exclusion principle, we consider C1 solutions where x is greater than equal to 9. So for this n of, okay, let me write it first here. C2 is uh, y greater than equal to 7, and C3 is Z greater than equal to 3. So this is, so for NC1, what we have is, we have, we'll just subtract 9 from both sides. So x plus y plus z equal to 15. Now we are saying that x can be written as x bar plus 9. So where here it was x greater than equal to 9, uh, y greater than equal to 0, z greater than equal to 0. In this case, we have 15. We can now write x bar greater than equal to 0, y greater than equal to 0, and z greater than equal to 0. So basically we subtract this 9. So it becomes x bar plus y plus z is equal to 6. So again, this is the sticks and stone problem. We have 6 plus 2, C2. So that would be 8, choose 2. So this is actually 17, choose 2 also, same thing. NC2 would be x, uh, or in x plus y plus z equal to 15, where y is greater than 7. So again, we'll have x plus y bar plus z equal to 8. We subtract 7 from both sides, where y bar is greater than equal to 0, and all others are also greater than equal to 0. So we have, again, for here we'll have um, 8 plus 2, choose 2, that is 10, choose 2. In C3 would be x plus y plus z bar. Z bar is greater than 3, so we'll subtract 3, so that would be 12, and z bar greater than 0. So again, that would be 12 plus 2 by 2, that is 14, choose 2. For n C1, C2 would, we'll have to take, so x plus y plus z equal to 15. Here we'll have to write uh, x greater than equal to 9 and y greater than equal to 7. So it is x bar plus 9, y bar plus 7 plus z equal to 15. So here x bar greater than 0, y bar greater than equal to 0, and z bar is already greater than equal to 0. So that gives us x bar plus y bar plus z bar should be 15 minus 16, which is minus 1. But since we are considering all of them to be positive, so this NC2, C1, C2 would turn out to be 0 eventually, because it is the sum of non-negative integers cannot be negative. So similarly, if we do NC1, C3, where I'm considering x to be greater than equal to uh, 9 and z to be greater than equal to 3. So 9 plus 3 is 12. So it would be x bar plus y plus z bar equal to 9 and 3, 12, and you have 3. So this would be 3 plus 2 by 2, that is 5, 2. And C2, C3 would be, again, we are considering y and z, so we are y bar plus z bar. So it is 7 plus 3, 10, and this 5. So this would be 5 plus 2 by 2. It is 7 by 2. And if we consider all of them, C1, C2, C3, it would be X bar plus Y bar plus Z bar, and we'll have to subtract 9 plus 7 plus 3, which is 19, it is minus 4. So this cannot be negative, so it is 0. So now if we substitute it, so basically n not C1, not C2, not C3 is n. So our n was all possible combination, that is 17 C2 minus, so minus we have 8 choose 2 for C1, then 10 choose 2 for C2, 14 choose 2 for C3, and now we'll have to add the doubles. So it is 0 for C1, C2. For C1, C3, it is 5 choose 2. For C2, C3, it is 7 choose 2. And finally, we subtract 0 for n C1, C2, C3. So if you substitute all this, I think the answer comes out to be 3, so which is the correct answer. So there are only 3 combinations of X, Y, Z such that X is non XYZ are non-negative. So this is the important point. XYZ is non-negative and they have this constraint. So that is how you get it. So that brings us to the end of our discussion. So if you have any questions related to what I have discussed or from the class notes, you can ask. If anyone, if no one has any doubt, we can close the session for today and we'll meet again on Monday to discuss week 11 assignments. So thank you for joining in, and again apologies for the change in class.
Thank you, sir.
And best of luck for the course. Yeah, we can leave.